AQA A-level physics. This is for the medical physics option, and this video is about imaging with radioisotopes. So basically you inject the patient with some radioactive substance, and part of that would be a radioactive isotope, and then this substance will naturally collect in certain organs, as we shall see, and when it decays it produces gamma photons, and then we detect these gamma photons outside the body using a gamma camera, and then a computer will produce an image for us. These are the isotopes mentioned in the specification, so you should learn a bit about them. The half-life technetium-99 is the most commonly used. 80 to 85% of all diagnostic imaging procedures use technetium-99. Why? Because it easily attaches to a wide range of chemicals. Therefore, you can target a variety of organs. The indium-111 used to label blood cells and antibodies. Iodine-131, remember iodine and the thyroid. It naturally collects in the thyroid. It's mostly used for therapy, for instance, for treating thyroid cancer, but you can also use it for imaging at the same time as well. Look at the energy of the gamma photons. With the iodine-131, you get a significant amount of high energy beta particles emitted as well. So the most commonly used is technetium-99. It's 99M, don't worry about that. Half-life about 6 hours. So it's long enough to take good images, but it won't do long-term damage. This is always the compromise. You want it to be active enough so that it gives off plenty of gamma, but then you don't want it in the body after you've actually taken your pictures. So that is always the compromise. 6 hours is good. When it decays, gamma photons are emitted along with low energy electrons. So another big consideration is the dose in sieverts or millisieverts that the patient gets. And if this stuff actually gave off high energy electrons or alpha particles, that would significantly increase the dose. But technetium-99 doesn't. The gamma photons can easily leave the body and can be accurately detected. And as I said, this isotope can be combined with a wide range of biologically active substances. So you can look at lots of different organs. Hospitals will have one of these things, a molybdenum technetium generator. So basically, the molybdenum-99 is produced in a nuclear reactor, and it has a half-life of 66 hours, and it decays to produce your technetium-99. So you have this generator, and looking inside, there's this aluminium oxide, which has got your molybdenum oxide in it. And it's called milking. So you put your saline, your salt solution in there, and that washes out the technetium. So you get your technetium oxide in solution, and then the whole thing is in a shield. And then every couple of weeks, it lasts up to 2 weeks, you send it back to the company and they will give you a fresh one, loaded with fresh molybdenum. This is a gamma camera. We need to know a bit about how this works. So you've got gamma photons working from the bottom upwards here. So you've got gamma photons. They go through a collimator, which is basically lots of lead tubes. And it's pretty obvious that the only gamma photons we'll get through are the ones which are approximately perpendicular to these tubes. This hits a scintillator. If you've been watching my other videos, you'll know what that does, produces flashes of light. And then your photomultiplier tubes kind of amplify the signal. And then the signal, I'll talk a bit more about this on the next slide, the signal goes to a computer, and then that can go to a monitor. So the photomultiplier tubes, we need to know this. Look at the diagram. So light from the scintillator hits a photocathode, and that produces a small amount of electrons, but then going from anode to anode to anode to anode, these things called dinodes, and each time it strikes one of these dinodes, you get more and more and more electrons until you get to the final anode, where you get, for each flash, you get loads and loads of electrons. So the electrons are generated at the photocathode, and then the electrons are accelerated by high voltages, and more electrons are generated on each collision with a dynode, and then the anode generates an electric charge that can be measured. Now, there are two reasons that the count rate will decrease with time. Now, one of them is the physical half-life. These substances, for example, I said the technetium has a half-life of 6 hours, but then there's also the biological half-life. So the substance that it's attached to will naturally be broken down, perhaps by the liver, and then excreted by the kidneys or through the intestines or whatever. So you've got the physical half-life and the biological half-life, and you may get a question where you have to work out the effective half-life, and it will be a combination of them. Look at that equation there, a little bit like resistors in parallel, isn't it? So here's a little question for you to do, typical kind of exam-y question. Stop the video, do it, and the answer is, there you go, 7.7 days. Positron emission tomography, need to know a little bit about that. Some isotopes decay by emitting a positron, which is a little bit of antimatter. It's a positive electron, okay? For example, carbon-14. Now, the positron will almost immediately be annihilated, because when antimatter and matter come together, they annihilate each other. So it will be annihilated by an orbital electron, and the mass will be converted into energy, and you'll get two gamma photons which will be emitted in opposite directions. Then both photons are detected, and what the computer does is it works out the time difference, and from the time difference of them being detected, it can calculate the location. So you do this in slices. So again, it's tomography. Remember, tomos means slice. So you do it for cross sections, and then all of this data can be combined into a 3D image. Carbon-14 I mentioned, that can be part of a glucose molecule, and then parts of the body where there's lots of respiration happening, or to look at blood flow. This technique produces high quality 3D images. It's very, very good for looking at soft tissues, apparently early detection of cancer, but the machines do cost a lot of money, so there's a high initial financial cost. Now, this isn't imaging, this is radiotherapy. I'm just tagging this on the end of this video. So radiotherapy, high doses of radiation can be used to destroy cancer cells and to shrink tumors. Okay, the cells that are most susceptible to radiation are the ones that do lots and lots of cell division, which is why, you know, in a gentleman, in his testicles, yes, because there's lots and lots of sperm production going on in there. On your skin, there's lots of mitosis going on, but also cancer cells, they divide rapidly. So cancer cells are actually more susceptible to radiation, ironically. So high doses of radiation can be used to destroy cancer cells. You can do it externally using a targeted beam, or you can do it internally by putting stuff inside the patient. So external beam therapy, so it's a beam of high energy X-rays, or you can use protons or electrons. If it's electrons, then that's limited to treating like skin cancer or cancer just below the skin. But to get deep inside the body, high energy X-rays. Now, to protect the patient, we want the tumor to get a very, very high dose, but we don't want the patient, the rest of the patient. So the beam is always aimed at the tumor, but then the whole machine rotates so that it's always pointing at the tumor, but then the rest of the body gets a very low dose. There would also be a significant amount of shielding, and the beam would be very, very collimated. So as I said, the tumour gets a very high dose, but the rest of the body, you are minimising the dose. Internal radiation therapy, so you can be a solid, and that's called brachytherapy, where you put seeds or ribbons or capsules actually in or near the tumour. This is commonly used to treat prostate cancer. So a very disturbing picture there, and they're putting these radioactive needles inside the prostate gland, and then they leave them there and they emit radiation and attack the cancer cells. Or it can be a liquid, and that's called systemic therapy. And this radioactive liquid, it might be swallowed, or very commonly it's in an intravenous line, and then this stuff travels through the blood, seeking out and killing cancer cells. So this is internal radiation therapy. And that's it. That's the end of this video, and that's my last medical physics video. So I hope you find them useful. For more information, there is an AQA document. If you Google Teaching Guide Medical Physics, and you'll get loads of information from there. And then obviously look at as many past papers as you can. So if you just go on the AQA, go on assessment resources for the A level, do paper 3 medical, and you'll get all of the available past papers and mark schemes. So anyway, good luck with that, and I hope you enjoyed those videos.